Module 6 will discuss the process for designing pavement for rehabilitation. So when we say rehabilitation, what do we mean? If we recall from Module 1, rehabilitation is the process of restoring a road for the purpose of repairing it and bringing it to a condition of structural and functional adequacy. Repair is typically needed due to some sort of distress within the pavement structure, and the most common one we see is cracking. This is usually cracking that's initiated from the surface of the road, which we refer to as top-down cracking. Rutting also plays a role, but the majority of our rehabilitation projects in this state are programmed because of the amount of cracking in the pavement. Milling and resurfacing is a process used to improve the structural condition of the existing roadway. The distressed pavement is removed by milling with a machine that has a rotating drum with teeth used to grind off the existing material, which can be set to a specific depth and cross slope. The exposed milled surface is then overlaid with new asphalt and lifts to bring remaining pavement to structural adequacy. The rehabilitation design process is summed up in a flowchart in the Flexible Pavement Design Manual. From this figure, we see that the first step in the process is to define your design objective. That goes back to knowing and understanding the scope of your project. Is this rehab project being done to provide structural improvement, or is it simply an operational type project, such as a skid hazard project or a pavement-only project? Once you know the purpose of your rehabilitation, you can start collecting some preliminary data from sources such as Pavement Condition Survey, the Roadway Characteristics Inventory, the straight line diagrams, and the as-built plans from the previous construction of your roadway. After evaluating the preliminary data, you'll be ready to move forward and request some additional data from different offices, including traffic data, existing pavement information, including distress types and the structural makeup of your pavement, field resilient modulus, and any other additional considerations there may be for your project. These may be best identified through discussions with your district maintenance and construction staff. And when your design is completed, you'll need to submit it for approval by the district design engineer. So looking a little more into each of these preliminary data sources, the Pavement Condition Survey, also known as the PCS, can be accessed through the department's pavement management webpage by going to www.fdot.gov/roadway/PM/PM.shtm. From the Pavement Management's homepage, click on Reports, and this will bring you to the webpage that has all the reports with the pavement condition history. So you can view interstate projects by either district level reports or by contractors, or you can view all state roads by selecting one of the counties in the lower portion. Let's look at a county report for an example. So clicking on Leon County will load up the report for all roads in Leon County. To help you navigate these reports, let's look at a few things. First, you'll want to find the column titles at the top of each page of the report. This explains everything that's included in each line of the report. You have things here such as roadway ID, begin and end mileposts, and the side of the road, right or left. You have the distress type, and you have the year that the pavement condition survey was performed. One thing to note here regarding the distress ratings in the survey, the years wrap around, so the ratings for a roadway segment will appear in 2 rows. There are lots of other pieces of information that are all helpful, but we'll just look at those few items for this training. So looking here at milepost 1.33 to 1.59, on the right side of State Road 263, we see where the column headings translate to down below. Here's the roadway ID, the milepost and roadway side, and then we have all of our distresses by year listed over here. Now what are these empty spaces here in the crack and ride ratings? Those are years that the pavement condition was not rated, usually due to a construction project. The road does not get rated during construction. For this particular roadway, it just so happens that there were 2 construction projects, one in 2000 and then another one in 2005. So if you look at the ratings in order of increasing years, you'll notice a decline in the crack and ride ratings. Then there's a blank year, and after that you should see a notable jump in the ratings, which indicates the improvements were made. One thing to note is on the left-hand side of the roadway information, you'll see some project numbers and contractor information. If you want to find out more about the gaps in pavement ratings, this is where you should look. This is information on the construction project that was done on the roadway segment that created the gap in the ratings. So here we can get the FPID, the milepost range, the fiscal year of the construction project, the work mix type, and the contractor. This is information you can use to find out more history on your project. The major takeaway from this form is that you can look at the history of a road and determine how it's performed. How many times has it been resurfaced? How long has it typically taken for the road to start showing deterioration? These are definitely things you'll need to keep in mind as you prepare your pavement design. The Roadway Characteristics Inventory, or RCI, is a collection of transportation features on all of our roads in the state highway system. Straight line diagrams are linear graphical representations of the features and characteristics from the RCI database along roadways on our state highway system. You can find all the straight line diagrams available for download at the website shown here on the screen. The straight line diagrams are a good tool for when you need an overview of your project location, the intersecting roads, number of lanes, bridges, culverts, and sometimes curve data, and everything is referenced to a milepost. This is a handy thing to take with you when you do your field review. As-built plans will provide you the most information about your project. This is what was actually recorded as being constructed at the time of the most recent construction project in your project area. Some specific things to look for are the pavement design information in the typical section sheets, including existing stabilization type and limits. You can also look at any specific areas of concern that you may need additional information on, such as locations of previous widenings. These areas may have different pavement thicknesses from the original travel lanes, and that's something you'll need to know when you're doing your resurfacing design. To get a copy of as-built plans for your project, you'll want to check with your department project manager. Once you've collected your preliminary data on your own, you should be ready to start coordinating with other offices to request more detailed data for your project. You'll want to request your design traffic data, which is where you'll get your design easel data, from your district planning office. The request for information on your existing pavement structure to determine layer types and thicknesses, and also any distresses such as crack depths, will go to your district materials office. Existing roadway information, including pavement widths, existing flush shoulder, curb, and gutter, cross slope, and any other constraints, is typically collected by your project surveyor, but sometimes may be collected during pre-design by the State Materials Office. And your resilient modulus value will come from deflection data obtained by the State Materials Office by way of falling weight deflectometer testing. When you request deflection data, it needs to be coordinated through a single contact within each district if possible. This will help with the logistics and scheduling of the State Materials Office FWD crew. I should also point out that we have some restrictions on where we want to collect deflection data. The 3 bullets shown here are locations where we typically do not request FWD data to be collected. This is because the distances are extremely short, or because the geometry of them make it extremely difficult to set up the necessary temporary traffic control to collect the deflection data. If you have a special need for your project, though, please be sure to communicate that with the State Pavement Evaluation Engineer at the State Materials Office. If you're not able to obtain deflection data for your specific project, there's another tool that can be used. The Falling Weight Deflectometer Dashboard is a GIS database of all the previous FWD data collected. If you're interested in using this tool, please contact someone at the State Pavement Management Office. You can find our contact information on our website. In general, you should be able to find a nearby location with deflection data within this GIS tool and use it to help make a decision on your existing resilient modulus value. You can combine this information from the dashboard along with other information you're collecting about your existing pavement structure and performance to arrive at a reasonable existing resilient modulus value. So this is a screenshot here of the FWD dashboard. You can see a map located on the right-hand side of the screen, and if you were to zoom in on the state of Florida, you would see a bunch of different colored line segments starting to appear. Each one of these line segments represents a deflection test that's been performed. So if you zoom in close to your project location, you can click on a road near your project and you'll see the test data. You'll be able to see the date that the FWD test was performed and also the recommended resilient modulus value. You'll need to coordinate with your district materials office on a few items. They are the ones who will be in charge of collecting pavement cores and having the evaluation done. They'll be able to provide you information on the distresses in the existing pavement structure, including the locations and extents or depths of each distress type. You'll receive information on the type, thickness, and condition of the pavement layers within each core. And you'll also receive cross-slope information along with any additional relevant history related to the pavement within your project limits. The District Materials Office will also provide recommendations on milling depths and limits, any cross-slope correction and overbuild recommendations, and binder selection. Please be sure to read through the report thoroughly and discuss any remaining issues with your materials office. The pavement evaluation information should be used by the designer to carefully evaluate the possible causes of the current distress, so that the distresses are not simply repaired, but are also prevented from rapidly reoccurring. The designer should not be satisfied with simply providing an adequate structural number, but should also consider other factors. An example would be an unstable lower layer that has repeatedly contributed to rutting in the past. By studying the pavement history, this problem could be identified and evaluated and a deeper milling depth set. A concrete overlay or reconstruction to concrete are other alternatives to consider. Just to show you a quick sample of what the pavement evaluation form looks like, this is one of the items you should receive in your PSER. This is where you'll find all the details of each pavement core. You'll see core numbers along with their location, and then each layer thickness and type is detailed for each core. Crack information, pavement condition, rut information, and cross-slope data should all be noted for each core. You should review all the pavement core information and develop an average existing pavement structure based on the core data. On a related note, if you want to learn more about the different pavement distress types, I highly recommend looking at the department's Pavement Condition Survey Handbook and also the FHWA Distress Identification Manual. The Pavement Condition Survey Handbook is found on the State Materials Office webpage under Documents and Publications, or you can go directly to the website shown here on this slide. This handbook describes the process used to conduct the pavement condition survey. For the FHWA manual, you should be able to find it easily by doing an internet search for the FHWA Distress Identification Manual. Both of these documents provide descriptions of each distress type, along with example pictures of the pavement distresses and levels of severity. You'll need to perform a field review. You need to be familiar with the pavement survey and evaluation report prior to going out into the field. This way you can identify specific locations you want to investigate further or just simply verify. Look for anything that has changed since the pavement survey was completed. For example, are there any locations that look like they've recently been patched? Be sure to take lots of pictures, but also make sure you write down where the picture was taken. All pavement photos end up looking very similar when you get back to the office. The need to mill all or part of the existing pavement should be evaluated for every project. A decision to mill should be based on sound economic and engineering principles. Consideration should also be given to time between coring and evaluation of the project and the construction phase of the project. If the project is cored and evaluated, but not constructed for several years, the pavement conditions and the pavement evaluation may change significantly. A few of the typical reasons for milling include removal of cracked asphalt. Ideally, cracked pavement should be milled out to avoid reflective cracking in the overlay. It's usually desirable to leave at least 3/4 of an inch of asphalt over the base throughout the project to protect it from traffic and rain. Under specific circumstances, the entire asphalt structure may be milled out, but this needs to be done in conjunction with contract provisions to provide for traffic control and protection of the base, such as placement of the first lift of structural asphalt no later than the day after the surface was milled. Cross-slope correction is another typical reason for milling. It's usually simpler to correct cross-slope using milling rather than variable depth paving. Allowing the contractor to place uniform lifts of asphalt will result in a better product. You may have a project that has specific grade requirements, such as presence of curb and gutter, or bridge approaches or underpasses. In these projects, milling may be a good tool for achieving proper roadway grade. Also, you may have an asphalt layer that is susceptible to rutting. This can be removed and rehabilitated by milling and overlaying with a stiffer mix. I also have a couple of milling considerations. The first one is related to scabbing. Scabbing occurs when the milled surface is not uniform. It typically happens when you mill too close to the top of an existing layer. The milling machine may chip up some larger pieces of asphalt in areas like this, and so it creates an uneven surface to overlay. These chipped out areas will result in future pavement performance issues due to bonding issues created by the milled surface. So to avoid this, you should try to either use a shallower mill depth, leaving maybe 3/4 of an inch of the existing layer, or else completely remove the existing layer. Leaving a 1/2 inch or less of an existing asphalt layer may result in scabbing and create future bonding and delamination issues. The example shown here on this slide gives us an idea of things to watch for. As you can see, the milling depth of 2.5 inches would not completely remove the existing Type S layer of asphalt. So when you have a situation like this, you'll need to work with your district bituminous engineer and your district construction office to determine if you should make your milling depth either a little more shallow or a little deeper in order to avoid scabbing. The other milling consideration is to keep your mill depths to 5 inches or less, if at all possible. An alternative to a deeper milling would be to consider a crack relief layer or additional overlay thickness. If you have a project where a deep mill may be necessary, you need to coordinate with your construction office to discuss the best alternative for your project. So now that you've collected all the data you need for your pavement design, including the resilient modulus, traffic data, and existing pavement structure, you're ready to do some calculations. The first number we'll look at is the existing structural number. This is the strength of your pavement structure as it exists in the field today. You calculate it based on the pavement core information you receive from your district materials office. When a pavement has been in service for some time, it can be demonstrated that the asphaltic materials have lost some of their load-carrying ability. To represent this in existing structural number calculations, a set of reduced layer coefficients reflecting the current pavement condition to be used for rehabilitation projects has been tabulated. These values are given in Table 7.1. So to calculate your existing structural number, it's just like the calculation we did in Module 4 for new construction. The only difference is that this time our layer coefficients for asphalt will come from Table 7.1, which are our reduced layer coefficients. When you review your pavement survey and evaluation report, you, as the pavement design engineer, will need to determine the average layer thicknesses that exist on your roadway. So remembering back to your pavement coring report, you'll need to review this report in its entirety and group the pavement cores into appropriate locations, typically by lane or by roadway direction, such as eastbound lane cores and westbound lane cores. This will depend on how many lanes you have. Also look at any turn lanes and median openings separately, as these areas typically have somewhat different pavement designs since they're often added at different times in the main line for operational type improvements. Be sure to watch out for any cores that are anomalies and use good engineering judgment to determine whether or not they should be included in your averaging for the overall existing pavement structure. So once you've identified your existing pavement structure, you're ready to move on to select your corresponding layer coefficients. Asphalt loses some of its load-carrying capacity over time, and so the department has developed the reduced layer coefficients for asphalt to account for this. These values, again, are found in Table 7.1, and they're based on the existing layer type and current condition of the pavement. As you can see, there are 3 different values listed for each layer type on this table: good, fair, and poor, with the good values being slightly higher than the poor values. And if you noticed on the pavement coring sheet, the survey provides a good, fair, or poor condition rating for each core. So again, using the data from this sheet to develop your average existing pavement layers, their thicknesses, and their condition is extremely important to your resurfacing design. For the existing base and stabilization, we assume that they remain at full strength, and so we don't reduce those layer coefficients for the existing structural number calculation. So to find the layer coefficients for base and stabilization, we still need to use Table 5.4 from Chapter 5. Let's look at how the existing structural number is affected by milling. If you have milling on your project, which most resurfacing projects do, then you need to know that the existing structural value of the layers that you mill out have to be subtracted from the overall existing structural number in your calculations. Let's look at a quick example. Let's say you have this existing pavement structure, and let's also say that it's in poor condition. Remember, this information comes from your pavement coring report. The first step in calculating the existing structural number is to determine the layer coefficient for each pavement layer. So for our asphalt layers, we look at Table 7.1, and since we said our pavement is in poor condition, we need to look at this far right-hand column for our values. The first layer is FC2, which is the older open-graded friction coarse mix, very similar to FC5, which has no structural value. So for FC2, even if it's in good condition, we still assign it a structural coefficient of 0. The next layer is type S, which we see has a value of 0.15, and our next 2 layers of type 1 and then binder also have a value of 0.15. Our next layers are the lime rock base and the stabilization, which we previously said are assumed to remain in sound structural condition, and so we need to look at Table 5.4 to get these structural coefficients, since we do not need to reduce them. So here we see that our lime rock base has a coefficient of 0.18, and our stabilization has a coefficient of 0.08. So now that we have all of our layer coefficients defined here, we can go ahead and calculate our existing structural number. So multiplying each layer thickness times its corresponding structural coefficient, we get these values. And now adding them all up, we see that our existing structural number for the entire pavement structure is 3.08. But wait, we forgot to account for our milling. So let's say that we're going to mill 2 inches of this pavement. If we remove 2 inches of the existing pavement structure, we can no longer account for that structural value in our existing structural number. So we need to subtract that value out. So first we find out what the total structural value of our milled layer is. In this case, it's 0 plus 0.23. So a total value of 0.23 is what we are removing by milling. Next, we need to subtract this value from the total existing structural number we previously calculated. So 3.08 minus our milled structural value of 0.23 will give us an existing structural value of 2.85, which accounts for milling out 2 inches of our existing pavement. Now let's take a step back and remember the other values we need to determine for our resurfacing project. We just calculated our existing structural number and accounted for the 2 inches of milling. Next, we need to find our required structural number. This is based on the AASHTO 93 design equation, so we need to know our design easels and our resilient modulus. So let's take a look at that. To find our required structural number, we can remember back to using the design tables in Module 4 for our new construction calculations. We'll find the required structural number for our resurfacing project in the exact same manner. So for this example, let's say we have a design easel of 4 million. Remember, this is a value you would actually need to get from your planning office. And for the sake of this example, let's pretend that the State Materials Office gave a resilient modulus recommendation of 11,000 psi based on their FWD testing. And as a designer, let's say that for this example project, we want to select a 94% reliability. Let's assume that this road is a rural arterial, and so the design easel of 4 million is fairly high volume for our facility. So we'll choose a slightly higher percent reliability because of the high traffic volume. So knowing these 3 factors, we now go to the appropriate design table, which in this case is table A6A. Looking down to 4 million easels and over to an 11,000 psi resilient modulus, we see that they intersect at the structural number of 3.94. So that's our required structural number. So now we have our existing structural number, and we've accounted for the milling in our calculations. We now have our required structural number, and so the last step is to determine our overlay structural number. This is the structural number that we'll need to bring our existing pavement structure, minus the milling, up to the value of our required structural number. Looking at the equation for the overlay structural number, we simply subtract the existing structural number, after milling, from the required structural number to determine the value of the structure that we need to replace after milling. So the values we just calculated for this would be 3.94 minus 2.85, which will give us an overlay structural number of 1.09. So whatever we use to resurface needs to have a structural value of at least 1.09. Another way at looking at this is to set the overlay structural number equal to a layer coefficient times the layer thickness. We already know what the overlay structural number is. That's the 1.09 that we just calculated. The layer coefficient is straightforward because we can look at table 5.4 and see that regardless of whether we select SP 9.5, 12.5, or 19.0, our layer coefficient will be 0.44 for our new structural asphalt. So that just leaves us with one unknown now, which is the layer thickness. So let's put some numbers into our equation. So we'll have 1.09 equals 0.44 times d sub o. Solving for d sub o, we get 2.48 inches as our required layer thickness of the overlay. Since asphalt lifts are generally in 1/2 inch increments, let's round that up to 2.5 inches. So now that we have all of our structural numbers calculated, we can finish up the pavement design. So for the purposes of this example, let's assume our project is a flush shoulder roadway. Also, let's remember that our design easel is 4 million, which means we have a traffic level C, which means we can use either a 9.5 mix or a 12.5 mix. If you remember from earlier modules, we're limited in using FC 9.5 and SP 9.5 mixes on traffic levels A, B, and C only, while 12.5 mixes can be used on any traffic level. But since we have traffic level C here, we're able to use either mix. So for this example, let's look at what our layers could be if our design speed was less than 50 miles an hour. Since we're less than 50 miles an hour, we can use a dense graded friction course. So let's try an FC 9.5 layer on top of our structural course. And since we know that our overlay thickness should be around 2.5 inches based on the calculations on the previous slide, then let's make an even 2 layers out of this. So the friction course will be 1¼ inches of FC 9.5, which gives us a structural value of 0.55 for that layer. The structural course will also be 1¼ inch thick, which will also provide us with a structural value of 0.55 for the layer. Adding both of the overlay layers together, we get a total overlay structural value of 1.1, which checks out since it's greater than the overlay structural number we previously calculated. Let's also make sure we're meeting our required structural number for the entire pavement structure. So if we add our newly calculated overlay structural number and the existing structural number for the pavement that will be remaining, we get a value of 3.95, which is greater than the required structural number of 3.94, so it checks out there too. So for this particular design, we have a design speed that's less than 50 miles an hour, we're milling 2 inches, and we're resurfacing with 2.5 inches, which means we're raising the profile grade of the roadway by a ½ inch. You'll need to make sure you don't have any vertical clearance issues throughout your project limits that could be impacted by the additional ½ inch of asphalt. So we previously determined that our overlay thickness needed to be 2.5 inches, but let's see how using open graded friction course might change things a little bit. Remember, that's 2.5 inches of structural value that we calculated, and open graded friction course does not provide any structural value, but it does add to our overall thickness. So let's take a look. If we were using a design speed of 50 miles an hour or greater, we would need to use FC5. It's always placed at a 3/4 of an inch thickness, and again provides no structural value to our pavement. So calculating that value is simple. The layer coefficient is 0. Moving on to our structural course now, we realize that our superpave will need to provide all the required overlay strength. So if we were to try to calculate the overlay structural number with FC5, but stick to our original thickness of just 2.5 inches, let's see what would happen. To provide a 2.5 inch overlay of structural course and friction course, we would use a 3/4 of an inch of FC5 and 1 3/4 of an inch of structural course. So 1.75 inches times 0.44 layer coefficient for the superpave yields 0.77. The overlay structural number for this configuration is 0 plus 0.77, so the total overlay strength of 0.77 is not what we're looking for. So you can either continue on with trying different superpave thicknesses until you reach an overlay structural number that's at least 1.09, or we can remember the calculation we just did a few minutes ago to determine the required thickness of the overlay and realize that it applies to the structural course layer here. So we know that our structural course layer has to be 2.5 inches thick. So to confirm, let's calculate it now. 2.5 inches times 0.44 equals 1.10. Checking this, we see that 1.10 is greater than our original overlay structural number, so we're good there. Finally, we see that it checks out with our required structural number as well. So for this version of the example of using a design speed of 50 miles an hour or greater and a mill depth of 2 inches results in a total overlay thickness of 3 1/4 of an inch. The same vertical clearance considerations apply to this scenario as they did to the last one. You will always need to check your designs to make sure that raising or lowering the profile grade of the roadway will not have any subsequent impacts to other design elements. I want to make sure to note that these are not the only combinations that would work. Pavement design is an iterative process, and you'll want to make sure to hone your design so that it's efficient while still providing the structural capacity to meet your expected design life. There are a few other considerations for rehabilitation design that I want to discuss. Overbuild is the first topic. Overbuild is additional asphalt that's placed at a specified cross slope and grade to correct existing cross slope or super elevation deficiencies. You should consult with your district materials office for recommendations with respect to overbuild. The details for overbuild are included in the standard specifications, section 334, and here are some specifics that I want to point out. All overbuild layers must be constructed with superpave at the same traffic level as used in the plans, so the asphalt used for the overbuild can and should be the same as the structural course that we use on the rest of the project. For uniform thickness overbuild, the allowable layer thicknesses are shown here, and these values match the allowable layer thicknesses for our regular structural courses. We do have different allowable layer thicknesses for our variable thickness overbuild layers though. As you can see here, the range is expanded for SB 9.5 on both the low and the high end. SB 12.5 may be placed at ½ inch thickness, but the top end remains at 3 inches. And the lower end of the range for SB 19.0 is also lower at 1½ inches, but the top end remains at 4 inches. Also, for variable thickness overbuild layers that use either SB 9.5 or 12.5, you have the option to taper this to 0 inches, but if you do this, you are required to place a minimum of 1½ inches of dense graded mix on top of it. This is for density requirements. The next item I want to discuss is cross-slope and super-elevation correction. The FDOT Design Manual provides the allowable ranges of existing cross-slopes that may remain for resurfacing projects, and it also provides 3R criteria for super-elevation. If your project's cross-slopes or super-elevation rates all meet criteria, then you don't have to make any corrections. However, if you're outside of any of the ranges and criteria in the FDM, you'll need to either go ahead and correct the cross-slope or super, which is the preferable approach, or else you'll need to process a design exception or variation, depending on the design speed of your road, for the existing condition to remain without correction. What you as the pavement design engineer really need to be aware of, especially if you're not the one doing the roadway design, is what mitigation strategies are called for in any design exception or variation for cross-slope or super elevation. One mitigation strategy might be to use an open graded friction course or a high friction surface treatment in order to alleviate the potential for wet weather crashes in areas of substandard cross-slope or super. If this is called for, then you need to absolutely make sure that your pavement design includes this mitigation strategy. Sometimes the existing cross-slope or super elevation could be so far outside of our criteria that it would be exceedingly costly to reconstruct the roadway to meet our new construction standards. So as an alternative, sometimes the mitigation strategy is to correct the deficiency enough so that it's at least back within the range that we would allow to remain for a 3R project. You would also need to be aware of this mitigation strategy since it will involve overbuild or a combination of milling and overbuild. If cross-slope or super elevation correction is deemed necessary on your project, you'll need to work closely with the roadway engineer for the project and your district construction office staff to make sure the design is constructible. Another consideration is binder selection. The department's standard binder grade is PG 67-22, which means the binder should be rut resistant up to temperatures of 67 degrees Celsius and crack resistant down to temperatures of -22 degrees Celsius. There are times when a modified binder should be used, and these are discussed in section 5.4 of the Flexible Manual. As a reminder for Module 1, a modified binder is either PG 76-22 or high polymer binder. So here are some instances where we want to specify a modified binder. You'll need to call for a PG 76-22 binder when an open graded friction course, so FC5, is used. In the top layer of structural course on roads that are traffic level D, which is a design easel range of 10 million to less than 30 million. It's used in the top 2 layers of structural course for traffic level E, which is a design easel of 30 million or greater. And it's used in FC 9.5 and 12.5 for traffic levels A through C, which is a design easel range that's less than 10 million. You should call for either PG 76-22 or high polymer for FC 12.5 in areas of traffic levels D or E. The reasons FC 9.5 isn't listed here for this category is, again, because it's not used on these higher traffic levels. And you should also use either PG 76-22 or high polymer in areas where you know you'll be having heavy traffic and slow-moving loads such as intersections and toll booths. The resilient modulus of asphalt is less under a slow-moving load than under a more dynamic high-speed load, which results in a higher potential for rutting. So that's why we suggest using the modified binders in these areas. On an older road that's been resurfaced several times, the computations may indicate that no additional structural course is required. In this case, you should remedy the problem by using the minimum amount of material appropriate for the distress. This should include a subjective consideration of reflective cracking potential that is not accounted for by the structural number calculations. If the ride of the existing pavement is poor, it may be desirable to provide sufficient structural asphalt to restore a smooth ride. Milling prior to overlay can also help improve the ride. The district bituminous engineer should be consulted for a recommendation in these cases. Document the basis for the overlay thickness regardless of exceeding the theoretical structural number requirements. This concludes Module 6, Pavement Design Process for Rehabilitation.